everyone. This is Dr. Sayyar, and I am going to talk about functions. Function is the main topic of college algebra course. Okay, in the first section, first chapter, we talk about definition of functions, and then some general properties of functions, and second chapter and third chapter we talk about different types of functions like polynomial functions, quadratic functions, maybe linear functions, exponential functions, and logarithmic functions. And then on the last chapter we talk about things related to functions. The concept of function is one of the most important concepts in mathematics, and you cannot really do mathematics without functions. Okay? So basically what we have usually are two variables. We call one variable x and the other variable y, and these two variables are related to one another. So there is a relationship between these two variables. Okay? But this relationship could be any kind of relationship, but we are interested in the kind of relationship with certain specific type of property that makes that relationship to be a function. Okay, so let's see what we have. We have two sets. So I draw a diagram like that. I call one of the sets x and one of the sets y. So here we go. A function from set x to y. So I write it like this function here. So set x has elements in it because the name of the set is x. The elements, I'm going to use lowercase letters for them. Let's say I have 1, 2, 3, 4, and 5 elements here. So I call them x1, x2, x3, x4, and x5. And elements of set y, naturally I'm going to call them by lower letter case y. So let's say I have 4 of them here. I don't have to have the same number of elements in both sets. So y1, y2, y3, and y4. Then get back to the definition. The function f from set x to another set y is a rule of correspondence, or rule that assigns or corresponds to each element x in set x exactly one element in set y, or a unique element, not more than one. You can't assign to each x value more than one element. Okay, so if I have something like let me draw another picture here so I can go together as I establish the definition. This is set x, this is set y. Let me maybe choose only 4 elements here and 5 elements there. So let me call this one x1, x2, x3, x4, y1, y2, y3, y4, y5. So let me do the function first and then non-function second. Let's say for the sake of definition, I'm assigning y1 to x1, assigning y2 to x2, assigning y2 to x3. I can do that. I can assign 2 different x values to the same y value. But what I cannot assign, what I cannot do as a function, let's say like here, I assign y1 to x1, then y2 to x2, and y3 to x2 as well, something like that. You see, you can't do this. You cannot assign 2 different y's. You can't assign 2 different y's to the same x. It has to be unique. So you can do 2 x's to 1 y, but not 1 x to 2 different y's. So this is basically not a function here. I don't even have to go any further. Not a function. Continuing here, let's say I assign y3 to x4 and y4 to x5. Okay, so is a function, but this is not a function. Even if I continue the rest of this like this, let's say, so this is a function, this is not a function. Okay, now let's look at these examples in the book. First example here, not example, this is just these three diagrams. I have my function f defined from set x to y, and then another relationship from x to y, and another from set x to y. The first one is a function. You see, I have elements x1 through x4. Maybe let me make this one a little bit bigger. There we go. I have elements x1 through x4 in my set x, and elements y1 through y3 in set y, and function f is defined by these arrows. So this is a function, you know, because all these assignments are unique. The second one clearly is not a function because I have two different assignments for x1, and the third one also is a function. Each assignment is unique. You see, this this y3 has been assigned to three different x values, which is okay. It's legitimate for the definition of a function. Okay? So this is another diagram that represents a function. y1 assigned to x1, y3 being assigned to x2, x3, x5, and y6 being assigned to x4. Okay. One terminology that we, I think, find it convenient to use is the terminology of x being the input and y being the output. You see, the idea is this: if you have if you think of a function as a box, like function f, then I put x in there, and output is y. Okay, so I call x the input and y is the output. This one, let's make it smaller again. So, like these are the input values, these are output values. Input value, output values. Okay, and one notation is the notation of, we call the function notation. Function notation basically says y equal to f of x. So what it says is that don't read this as f times x. Okay, that's not what it means. It means that y is the output, the unique output related to input x by function f. For example, when you put x into the function, y comes out, y is f of x. So you put x in there, f of x comes out. Let's say you put z in there, then f of z comes out. Whatever you put in, f of that comes in. Like if you put, let's say, 1 in there, 1, and then f of 1 comes out. You see, so it depends what you put in, f of that would come out. So they call it function notation. For example, here, if I go back to this diagram I have here, so this is my set x, this is set y, and this is function f. You see, y1 is f of x1, y2 is f of x2, and it is also f of x3. y3 is f of x4, and y4 is f of x5. y5 is f of nothing. Okay, so like here again, in this example, y1 is f of x1, y2 is f of x2, y3 is f of x3, and the same thing here, y1 is f of x1, y3 is f of x2, f of x3, f of x5, and y6 is f of x4. Okay, two terminologies, or two concepts actually, are the concepts of domain and range. The domain of a function is a set of all legitimate x values, those x values for which there is a well-defined y value. So if there is an x value in your in set x that doesn't have any y value, that value is not in the domain. The range is a set of all the y values for which you have an x value. So if you have a y value that doesn't have an x value, then it's not a domain. Let's show you an example. Let's say I have an x6 here. You see, this x6 doesn't have any y value, so it's not in the domain. This y5 doesn't have any x value, so it's not in the range. You see, not in the range. This one not in the domain. Okay, and if your function is defined by a diagram like this, it's very easy to determine what domain and range is. Like here, let's go back to this example. The domain of this function is set of all these x values. You see, x1, x2, x3, x4. Range is set of y1, y2, y3. This is not a function, so I'm not interested in defining domain and range for it. We could, but it's not a useful one. So this one, the domain is x1 through x5. It's a domain, and the range is just y1, y3, y6, y1, y3, y6. The other y values don't have any x values that they correspond to. Okay. The next thing we discuss is the presentation of functions. The presentation of functions. A function can have different presentation, like diagram presentation, and then table presentation, or set of order presentation. We can. These three presentations are useful actually for understanding and describing a function. But when it comes to calculations and modeling, really these won't have very much values. And we have to look for another type of presentation for them, which are algebraic equation presentation or graph presentations. We're going to see examples of this type of function presentations on the next few pages. But to continue this, you see, if I want to, let's say this example right here, right here. I want to do a table presentation. You see, what you do, basically you draw a table like this, you write the name of the function on the top, and then you put x here and y there, and you put all of your x values, like x1, x2, x3, x4, and x5. That's the one in the domain. Here x6 is not in the domain, see? And then the set of y values right in front of them. So x1 has y1, x2 has y2, x3 has y2, x4 has y3, and x5 has y4. You see, this is the table presentation of the same function. Another type of presentation is a set of order pairs. Basically what we have is we write x, the first number is x, the input, and y is the output, and we put them together and separate them by a comma, and we put parentheses around them. I guess maybe I forgot to mention something. Let me do that first before I continue. The x values are referred to as the input. I think I said that. Maybe I did, yeah. And y values are referred to as the output. So a function basically says each input has a unique output. Okay, so if you want to use that. So, but let's continue this. If I want to use the order pair as a presentation for this function, all you do is to say f is equal to, you see, x1, y1, so you write x1, comma, y2, y1, x2, y2, x3, y2, and x4, y3, and x5, y4. So you see, I have one function here. I present it by three different ways to present it: diagram, table, or order presentation. Okay. And as I said, if you have very many, like if you have 1,000 input and 1,000 output, then this is going to really be not convenient to show this way because you don't have enough room to represent. So this is nice if you have just a few input and output, so you can actually spell out all of them. So one example on this page is example 1. I have two sets involved. One set X consists of some well-known cars that we all know about, like Camry, Corolla, Accord, Civic, and Impala. And set Y are some manufacturing company manufactured some of these cars: Toyota, Honda, Chevrolet, and Mercedes. So what I would do is to write my X values, the set X and the set Y value, and then connect these or relate these by the common knowledge we have about these cars and their corresponding factories. Like we know that Camry and Corolla are manufactured by Toyota, Accord and Civic manufactured by Honda, and Impala manufactured by Chevrolet. So I don't have any cars here manufactured by Mercedes. So based on the definition, all these assignments are unique. So if I call this relationship H is a function. And the domain is Camry, Corolla, Accord, Civic, Impala, and the range is Toyota, Honda, and Civic. We have a couple more examples coming up on the next page. Okay, the second example we're going to discuss here today is the following. We have two sets, X and Y. X is the set of three guys here, Joe, Todd, and Matt. And set Y consists of these courses: algebra, biology, sociology, and English. And so this is set X and this is set Y. So I have Joe, Todd, and Matt. And here I have algebra, biology, sociology, and English. And let's draw the relationship between these two sets the way it's been described in this sentence here. You know that Joe is taking algebra and English. So Joe is taking algebra and Joe is taking English. And Todd is taking sociology and Matt is taking Matt is taking biology and English. So Matt is taking biology and English. Clearly this relationship here not a function, because each input, for example Joe, J, corresponds to two different outputs. Okay, so not a function. Now, as I advertised, the next example is a situation when a function can be described by a table. So we have two tables here. We're going to determine which one represents a function and which one does not. Like table F, these are the X values and these are the Y values. So X is 0, 2, 4, minus 1, 10, 2, and these are the Y values. And according to this table, 3 is assigned to 0, 4 to 2, 7 to 4, 9 to -1, nothing to 3, 11 to 10, and 17 to 2. And clearly this is not a function, simply because these two here has been assigned two different ones. So input 2 has two different output values. However, the second one is, because these are the X values, again these are the Y values, and each X has one and only one Y value, so this is a function. See, neither one of these values in this row is repeated. Here 2 is repeated. Because it's repeated, then it cannot be a function. So G is a function. 4 is not in the range because there is no x value. You see, there is no x value. 57 and 68, and again 70 is not in the range because it doesn't have any x value. The next example is the example in which some relations are functions and they are instead of ordered pairs. Okay, so here again, as I said before, the first numbers represent the x values, the second number represents the corresponding y values. So for example, 1 is assigned to 2, 0 to 3, 5 to -1, 7 to 4, and 4 to -3. Is f a function? We say yes. F is a function because each x value has one and only one y value. So neither one of these x values are repeated. Okay. The domain would be set up all the x values like 2, 3, -1, 4, 2, -3, -1, 4, and -3. And range, set up the y values. 1, 0, 5, 7, and 4. The next example basically is the same one. I should have used different numbers, but you know, it's the same thing except it's pair -3 and 4. So I want to change it a little bit. So I want to change this 7 to 1. I want to change the 7 to 1 to make it interesting. So this is my black pen. I cannot see it. So let's see. Let's change this 7 to 1 for the sake of make it a little bit interesting example. So I have 2 and 1, 3 and 0, -1 and 5, 4 and 1. G is a function because no x value has been repeated more than once. Okay, and but as you can see, the input 2 and 4, they can have the same y value. So y, that's why I changed this to 1 to make a point here. The y values can be repeated, but x values cannot be repeated because it won't be a function. So G is a function. The domain would be 2, 3, -1, and 4, and range is 1, 0, 5. You don't repeat 1, you just write it not more than one time. Okay. The next example, H is not a function because this input 4 is repeated twice. You have 4 has output 1 and 4 has output -1. So I say input 4 has 2 different outputs. 2 different outputs, 1 and -1. So that's a violation of function. So it's not a function, but it's a relation. All of them are relations. So every example is a relation. But we are interested in those relations with that defined to be they are functions. Okay, so a function is a relation, but a relation may not be a function. Now, as I discussed before, for the remainder of this course, we're going to have functions which are represented by algebraic equations. So this is what this page discusses, that idea. We have algebraic equations mean we have an equality. We have an equality. And we have something on the left side, something on the right side, some expressions in terms of x and y here, some expression in terms of x and y there. Then we're going to see if whether this equation represents a function. Okay. Usually x in that equation represents the x value, y represents the y value, and the value is for x and y are real numbers in this type of equation. When we talk about equations, we have to have numbers. We cannot put names like Todd, Joe, or Toyota, or Camry in it. So it has to be numbers. So as I said here, in this case the domain is a set of all real numbers, so that means x values could be from minus infinity to infinity or part of it. And sometimes they tell you what the domain is. Sometimes we have to determine the domain based on what the definition of the function is, and we're going to discuss this on the next few pages. So the question is, how do I determine whether a given equation represents a function? To answer that, we say, go ahead, solve that equation for y in terms of x. In other words, use intermediate algebra knowledge that you learn to isolate y on one side and everything else in terms of x and numbers on the other side. Okay. Then we look at that, and if we get one single formula or one single equation for y, then it would be a function. If we have more than one equation, then it won't be a function. Okay, so we're gonna have y by itself on the left side and everything else on the other side. So what's going to happen? Sometimes we have square that we have to take square root. So every time you take square root of something, then you're going to have plus and minus. For example, if I have let's say u squared equal to 4, then the question is, what is u? U is square root of 4. Of course I have to use plus or minus, so I get plus or minus 2. So if I have u equal to 2, is square, you get 4. If I have u equal to negative 2, you square it, you get 4. So when you take the square root of something, then you get two different answers, one positive, one negative. However, if you have cube and you take the cube root, you don't get more than one answer. You don't get plus or minus. In fact, every time you take even roots, like square root, which is the second root, or fourth root, or sixth, or eighth root, or so forth, you get always plus and minus. But if you take a cube root, you get only one answer. So let's see how this idea plays in our examples. Like we have one equation here, 2x minus y equal to 7. We want to see whether this is this relation between x, y represents a function. So what we do, we solve this equation for y. So in order to do that, because y is negative, I add y to both sides. So I get 2x, these two cancel out, equal to 7 plus y. Then I subtract 7 from both sides. These two cancel out, I get 2x minus 7 equal to y. We usually write y first on the left side, and then so I rewrite this as y equal to 2x minus 7. So clearly this is one formula. So each x value produces one y value. For example, if x is 1, for example, this is just one example. If x is 1, then you get one value for it. So I put 1 for x, I get 2 times 1 minus 7, so you get minus 5. So if I choose any x value, you get one value. So this is a function. So a function. So I call it f of x equal to 2x minus 7. See? Now let's look at the second example. We have x plus y squared equal to 16. In order to get y by itself, I subtract x from both sides. This x cancels this x. We get y squared equal to 16 minus x. Then you take the square root of both sides. You get y equal to square root of 16 minus x. As I explained above here, when you take square root, you get plus and minus. So clearly, I get two values every time I choose an x value. For example, if I choose x equal to, so each x value will have two different y values. For example, if x is equal to, let's say, 7. If x is equal to 7, then y is plus and minus square root of 16 minus 7, plus or minus square root of 16 minus 7 is 9, so you get plus or minus 3. So so actually, if you write this as pair, you have 7 and 3, 7 and negative 3, and that's clearly violation of a function, so not a function, because each x value will have two y values. One more example before we go to the next page is this one. To solve for y, I subtract 2x cubed from both sides, and I add 2 to both sides. So what happens, this 2x squared cancels this, 2 cancels negative 2, so on the left side I'll be left with y, and the right side I get negative 2x cubed plus 2, and this is one formula. So that means it's a function, because every x produces one and only one y value. Okay, well, sorry, this is already written here, so let me explain what I've done. This next example, I have x cubed plus y cubed equal to 9. We're going to determine whether this equation represents a function. We have to solve this equation for y in terms of x. So first I isolate y cubed, then I take cube root to get y by itself. So I subtract x cubed from both sides. These two cancel out. I would get y cubed equal to 9 minus x cubed. And then I take this the cube root of both sides. I get y equal to cube root of 9 minus x cubed, and notice that I don't have plus or minus here because I'm taking an odd root, the third root. So clearly this is a function, because each x value will have one value only. So it doesn't matter what you choose for x, you always get one value for y. So this is a function. So I can call this one y equal to, or f of x equal to cube root of 9 minus x squared. If I go back to the previous page, by the way, like here, this is a function, and the one in the bottom is a function. So I can call it like f of x equal to negative 2x cubed plus 2. So every time it's a function, I use the function notation, which is a very convenient notation for the sake of calculations. Next example, we have x squared plus y squared equals to 25. As usual, we have to isolate y squared first and then take the square root. So I subtract x squared from both sides. cancel out, I would get y squared equal to 25 minus x squared. Now I have to take the square root. If I take the square root, I get y equal to plus and minus 25 minus x squared. So I have two formulas. So that means each x value will have two different y values. That's why it's not a function. So that's not a function. Not a function. Because if you choose any x value, you get two of them, one plus with one minus. So now the next example, we are given a function, you see, y by itself on the left side and everything else in terms of x on the right side. So that means every x value produces one y value. So this is a legitimate function. And we're going to use this notation y equal to f of x, which is a very convenient one to do certain work with f of x. So the question is, what is f of negative 2? What that means is that if I replace x by 2, if the input is negative 2, what is the output? Output y. So all you do is to replace this x here for f of x by negative 2. So you get, I use parentheses, negative 2 squared. I replace x by negative 2 plus negative 2 plus 1. So you get 4 minus 2 plus 1. 4 and 1 is 5, minus 2 is 3. So what we have, the y value, if the x value is negative 2, the y value is 3. You see? The next one, f of 5. f of 5 means replace x by 5. So you have 5 squared plus 5 minus 1. If you notice, I'm using parentheses. The reason I use parentheses is to prevent unforced errors. Unforced error, what do I mean by that? Like, you know, if I didn't use parentheses, I would have written like negative 2 to power 2, and then without any paying attention, I would put it in my calculator, for example, and I say with negative 2 squared. And if you do that, if you type it like this in your calculator, you get negative 4, which is wrong. What I need is parentheses negative 2, all of it squared, which is will give you 4, and that's what we want. That's what we want. So every time you are substituting x or any other variable by a number, first use parentheses. So make sure to, in order to avoid this kind of errors. So continuing this, 5 squared is 25 plus 5 minus 1. 25 plus 5 is 30 minus 1 is 29. So if the x value is 5, the y value is 29. And f of t plus 1, that means now the input is t plus 1, whatever t is. It doesn't matter. T is a real number, therefore t plus 1 is also a real number. So what happens here is that if I have x, these are the x values, but if I put t plus 1, that means I have to replace all these x's by t plus 1. So we get t plus 1 squared, you see, t plus 1 for x, plus t plus 1 just for x here, no square, and then minus 1. Basically, we are done, but we have to continue this to simplify it to the simplest form. That's what we usually do. You do in mathematics. You always have to simplify to put it in the simplest form as simple as possible. So t plus 1 squared is t plus 1 times t plus 1, and then another t plus 1 and minus 1. Then you have to FOIL this. You see, t times t is t squared times 1 is plus t, 1 times t is another t, and 1 times 1 is 1. And then I have a plus outside of this parentheses. That means we can safely remove the parentheses and don't change anything about the sign of t or 1. So I just say t plus 1, and then finally this negative 1 at the end. Now simplify. T squared, that's the only one you have. Then I have a t here, t here, t here. There are 3 of them, so you get 3 t's. Then I have a 1 and 1, 2 and minus 1, you get 1, and that's the end of this. F of 2 over x simply says that look at f of x, and everywhere you see x, replace it by 2 over x. So all the x's become 2 over x. So this is going to be 2 over x squared plus 2 over x minus 1. So we are basically done. As I said, for example C here, I have to simplify this to the lowest form. So if I square this, I get 4 over x squared plus 2 over x minus 1. Now we have to do the common denominator. The common denominator is x squared. So I have 4 over x squared plus, to make x to become x squared, you multiply the numerator and denominator by x, so you get 2x over x squared. And 1 is actually 1 over 1, so to make it x squared, you have to multiply both of these two ones by x squared. So minus x squared over x squared. The reason I did that is because now you have the like denominators, so you write that, and you put the numerators together according to the sign that you see. So it's going to be 4 plus 2x minus x squared, and that's it. End of this problem. This example is basically similar. What we have, we are given 2 functions f and g, and we are asked to compute the value of f of 1 plus 2 times value of g of 3. So what we need to do is to find f of 1 and g of 3 first. Okay, and after we compute these two items separately, then put them together to get this whole thing. So f of 1. F of 1 means in f, which is right here, replace x by 1. So we get 1 minus 3 plus 7, so this is 5. G of 3. G of 3 is, replace 3 for x, you get the square root of 3 times 3 plus 7. You get the square root of 9 plus 7 is 16, so you get 4. So I computed both of these two guys. So f of 1 plus 2 g of 3 is f of 1. F of 1 is 5 plus 2 times g of 3, which is 4. So you have 5 plus 8, so you get 13. Okay. This next example, actually, I don't want to do it. This is something that we do in calculus, so at this point I really don't want to do this, so don't worry about it. So this exercise, which is also related to this example, we won't do. So, but the next example is an interesting one. We are given 2 functions f and g, and part A is asking us find the x values whose y value is 0. See, f of x equal to 0, so what is x value? So that means for what x value has the corresponding value of y equal to 0. So y is equal to 0. The question is x equal to what? That's what we have, see. So this is actually y equal to, see, y equal to f of x, or y equal to g of x. So to get this x, you replace y by 0. That's what we have. So y equal to 0 means f of x equal to 0, and f of x is this whole expressions here, 2x squared plus 5x minus 7 equal to 0. Now we have to solve this equation for x. This is an equation. This is a so-called quadratic equation. I don't know if you remember. So let me explain it separately here. You see, a quadratic equation looks like this: sum a times x squared plus some number b times x plus another number c equal to 0. We call this a quadratic equation. To solve this equation for x, unknown x, we can either factor it, but factorization may not always be possible. If we can't factor, we can use the so-called quadratic formula, which is minus b plus or minus square root of b squared minus 4 times a times c divided by 2 times a. And I hope you remember this. This is called the quadratic formula. So all you have to do is to figure out what your a, b, c are, put them in this formula to get values of it. So let's do it right here. In this case, a is 2, b is 5, and c is negative 7. So x is minus b minus 5 plus and minus b squared, which is 5 squared, minus 4 times a, which is 2 times c negative 7 divided by 2 times a, which is 2. When I have this radical sign, I just extend it all the way, and then I kind of draw it downward like that to know what the whole thing which is under the radical sign. Sometimes people do not write that. Sometimes people write like this: 5 squared minus 4 times 2 times negative 7. You see, this is not good, because sometimes you put 7 outside, and then this is another unforced error. You see, so to make sure you're doing this whole thing, just extend this radical sign and just go down. But that means all of this is under the radical sign. So when you put it in your calculator or whatever else you do, you make sure you consider the whole thing, not just part of it. So this is equal to, continue, minus 5 plus and minus 5 squared is 25, and then you have a negative here, another negative. When you multiply, you get positive, and 2 times 4 is 8, 8 times 7 56 divided by 4. And if you do this simple calculation, minus 5 plus or minus, you get 81 over 4, and we know that the square root of 81 is 9, so you get minus 5 plus or minus 9 over 4. So that means I have to do this twice, one time with plus. So if I have minus 5 plus 9, you get 4 over 4, you get 1. And if you use minus 5 minus 9, you get minus 14 over 4. That simplifies to negative 7 over 2, which is negative 3.5. So basically what it says, I have 1 and 0, so x value 1 gives the y value 0, and negative 3.5 also gives the y value 0. That's what we have. Okay. The second example is basically similar, but asking for the value of x which share the same y value. Whatever that y value is, we really don't care. but whatever it is the same thing for both function f and g. So we want to know what x value would do that, produce the same y value for both of these two. So y of the function f must be equal to y of function g. So you put both these two equal, and it becomes similar to this problem, a quadratic equation that you can solve it for x, and that would be your answer. So f of x equal to g of x. F of x is 2x squared plus 5x minus 7 equal to g of x, and g of x is 2x minus 2. And as I discussed here, quadratic equation, you know the right side or one side has to be 0. So in order to get that, you have to subtract 2x from both sides and add 2 to both sides. So these two cancel out, these two cancel out. You get 0. And then right side you have 2x squared, then 5x and negative 2x gives you 3x, and then negative 7 and 2 gives you negative 5. So that's what we have. Then you have to solve this for x. So in this case a is 2, b is 3, and c is negative 5. So if you put this in quadratic formula, x equal to the quadratic formula minus b plus or minus b squared minus 4ac divided by 2a. So we have minus b minus 3 plus and minus square root of 3 squared minus 4 times a, which is 2 times c negative 5 divided by 2 times a, which is 2. So if I continue this, you get negative 3 plus or minus square root of 3 squared is 9, and then minus times minus is plus. 4 times 2 is 8, 8 times 5 is 40 divided by 4. So negative 3 plus or minus square root of 49 divided by 4, and we all know that the square root of 49 is 7, so negative 3 plus or minus 7 divided by 4. Again, as before, if I choose plus, negative 3 plus 7 is 4, 4 over 4, we get 1. If we choose minus, negative 3 minus 7 is negative 10, negative 10 over 4 gives you negative 2.5. So if you choose x equal to 1, then g of 1 is equal to f of 1. That means the y value of f and g are the same for the input value of x. The same thing for input value negative 2.5. Okay. The next example, or actually concept, is the concept of piecewise functions. As the name suggests, piecewise function means this function has pieces. Okay, so what does that mean? That means the function is defined by different formulas or different recipes according to what the values of x are. Like in this example here, x could be less than negative 1, or x could be bigger than negative 1. So negative 1 is the border point. So sometimes x is less than negative 1, sometimes x could be bigger than negative 1. So if you choose an x less than negative 1 and you want to find the y value of that x value, you have to use this formula number 1. If your x value is bigger than negative 1, then you have to use this formula. You cannot use both of them, because if you use both, then you will have two different y values for the same x values, and that would be the violation of a function. Okay, so like f of -2, clearly your x is -2 and is less than -1. You see, less than -1. So I use this formula. So this is equal to -2 squared minus 1. You get 4 minus 1, you get 3. So you have -2 and 3 for this function, for this value. If you want to find the y value of input value -1, you see the equality is for the first formula here, equality. So I have to use this formula. So this is going to be equal to -1 squared minus 1. So this you get 1 minus 1, you get 0. So you have -1 and 0 for this one. f of 3, clearly 3 is bigger than -1. You see, bigger than -1. So what you do, you have to use the second formula. 2 times 3 plus 1, this is 6 plus 1 is 7. So you have 3 and 7. But g, similar. G of -2 here, the border value is 0. So depending upon whether your x value is less than 0 or bigger than or equal to 0, you have to use one of these two formulas accordingly. So g of -2. -2 is less than 0, so I have to use the first formula. So this is going to be equal to 2 times -2 minus 1. You get -4 minus 1. You get -5. So you have -2 and -5. G of 0. You see, 0 is included here, equal to 0, bigger than or equal to 0. You have to use this formula. So this becomes, I have to use the second one. So this is equal to -3 times 0 plus 5, and you get 0 plus 5, you get 5. So you have 0 and 5. Finally, this last one, g of 4. 4 is bigger than 0. You see, x bigger than 0, 4 is bigger than 0, so I have to use this one. So it's going to be equal to -3 times 4 plus 5, -12 plus 5, you get -7. So I have 4 and -7. Alright, let's continue this. The next concept, well, it's not a new concept, it's already discussed, the concept of domain. But the idea is to find the domain of a function which is defined by an algebraic equation. Because, well, first of all, domain means set of all the input values. All the input values for which there is a meaningful y value. So if there is an x value and there are no y values defined for that x value, then that x value, it will not be in the domain. If you have your functions defined by a diagram or a table or by a set of ordered pairs, that's quite straightforward to find the domain and the range as well, because you actually can see all your possible x values, because not too many of them, and then you can see the corresponding y values, and then you can tell what x value has a well-defined y value, and then you can write your domain, and also you can write your range. But it becomes a little bit tricky when your function is defined by a set of by an algebraic equation, because in that case the domain may contain infinitely many x values. So really, sometimes it's difficult to spell out all the possible x values. because the domain could be part of the real line minus infinity or infinity, or all of it probably sometimes. Everything from minus infinity to infinity, sometimes part of it. Of course, how do we decide what part of real line is the domain? That depends on the definition of the function, of the formula of the function, which put restriction on the domain. Okay, so the best way to discuss this is to do it actually by some examples. Okay, here are some examples. We have this first example is a formula that gives the volume of a sphere if the radius is given. Well, of course we know what a sphere is. This is a sphere like this. This is a sphere, and sphere has a center and a radius. Radius is r, and then the volume v. We use v and r, v for volume and r for radius, but we don't have to use these letters. If you want to put it in a more familiar form, I can use x, I can use y for the volume and x for the radius. So every radius x represents the volume of a single sphere. So this formula is actually a function. So if I write it in terms of y, see, y equal to 4/3 pi x cubed. I don't have to use v and r. I can use y and x to put it in more familiar form of a function. But this is clearly a function because every x value or every radius will produce the volume of one single sphere. So this is a function, clearly. Okay, then the domain. What is the domain of this? So what we have to figure out is what values for x are acceptable, and those acceptable values for x will constitute the domain. So clearly x is the radius and cannot be negative. So I must have x bigger than or equal to 0. You see, so that means that's your domain. The domain consists of all the real numbers bigger than or equal to 0. So actually we can graph it, you see. So if I put 0 here, because I have equality, I can use a solid line, solid point, call it 0, and I want every value bigger than 0. That would be everything to the right here. So the domain is actually all of that to infinity. So I can write it in two different ways. Domain is equal to set of all x's such that x bigger than or equal to 0. This is called the set builder notation. Or I can use interval notation, and because this endpoint 0 is included, I use bracket 0 to infinity, and because infinity is not a number to include, so I put parentheses around it like that. So you can either, so this means all the numbers between 0 and infinity including 0. So that's your domain, and this is the picture of it. Okay. So the restriction in this example was the fact that x had to be positive or 0 or non-negative. The next example is this function, the square root. And from previous class we learned that if I have a square root and if I have a u, a number u under the square root, u has to be bigger than or equal to 0. In other words, you cannot have negative number under the radical sign. If you have negative number under a radical sign with square root, then it won't be a real number, it would be a complex number. For example, you cannot have -4, you see, because this becomes complex number, but you're going to have real number. So we always demand, in college algebra, we always demand that the number under the radical sign to be bigger than or equal to 0. And that's the restriction every time you have a square root. Okay, so in this case, must have, you see, minus 1 bigger than or equal to 0. Just this whole thing under the radical sign. So that's a requirement. Otherwise, the function will not be defined. Then what we do, we go ahead and solve this for x just like an equation. So I add 1 to both sides. These two cancel out. You get 2x bigger than or equal to 0. I mean, bigger than or equal to 1. Sorry. And then you divide by 2. You get x bigger than or equal to 1/2. So that means for this function, values bigger than or equal to 1/2 are acceptable. Okay. So if you want to draw the graph of your domain, just choose one point here, solid point, because you have equality as 1/2, and then x bigger or equal to 1/2 says everything to the right, everything bigger than 1/2. So this would be your domain. And again, if you want to write it, you can write d equal to domain all x values such that x bigger than or equal to 1/2 is a set builder notation, or I can use interval notation 1/2 to infinity. Okay. In some of the homework, this notation is being used. In some other ones, this notation, and the test, maybe I usually use interval notation. Okay. Let me do another example of example involving radical sign. Let's say you have something like f of x square root of 3 minus 5x, something like that. You want to find the domain of this function. So we say must have 3 minus 5x bigger than or equal to 0. That's the requirement. And to solve for x, you subtract 3 from both sides. You get negative 5x bigger than or equal to negative 3. Now you have to divide by negative 5. Because you have to divide by a negative, then the order of inequality will switch to the opposite direction. So these two cancel out, you get x. Now instead of bigger, then you get less than or equal to negative, of course, divided by negative 5. Sorry about that. 3/5. So that means all the values less than or equal to 3/5 are acceptable. So if I choose one point here as my value 3/5, and then less than or equal to that means everything to the left side. So the domain would be here, minus infinity. So again, if you use the set builder notation, then you say domain is from negative infinity to 3/5, which is the same thing to say set of all x's such that x less than or equal to 3/5. Okay. So this was another example. So sometimes, you know, when you solve these inequalities, you have to make sure what you have. If you divide by a positive number, you don't change the inequality, but if you divide by a negative number, you have to change the order of the inequality. Okay. So, before I do the next example, let me do a simpler one first, and then get to this example B. Let's say you want to find a domain of a function like, let's use a different letter, g of x equal to x over x minus 3. That is something very simple. Okay. So the question is this. First of all, this is the function, because no matter what you choose for x, we always get one y value for it. So the question is there any value for x which for which the function is not defined? Then you say yes. If you have a fraction, you never want the denominator to be equal to 0. So you say we do not want x minus 3 to be equal to 0. We don't want the denominator to be equal to 0. Which, if we solve it for x, x is 3. So that means we don't want x equal to 3. Everything else is okay. Okay. So what is the domain then? First of all, if you go ahead and graph it, because I have to remove this value. This is a bad value. You see, we don't want it. So for that reason, I use a point here, and then there are hollow point. Hollow means 3 is not there anymore, it's removed. Then everything else left would be the domain, which is on the left side and on the right side. So something like this, you see. I use parentheses to indicate that this point is not included. So in this case, the domain is all the x values such that x is not equal to 3. Everything except 3, which is equal to, I can go from negative infinity all the way to 3, and then I use parentheses. That means 3 is not included. Then it's together with from 3 to infinity. And then I have to join this. I use a symbol U to say that this set together with that one, and then because I use parentheses, 3 is not included. So this is the interval notation for you. Okay. So in this case, we had one value, bad value, that we had to remove. Sometimes you have more than one value that we have to remove. Like this example here is a similar concept. We say we do not want x squared minus 5x plus 4 to be equal to 0. So I have to find the x values that makes this one equal to 0. This is again another quadratic equation. Like if I can find it again, where is it? Right here, you see, another quadratic equation. I have to solve it for x. I can use the quadratic formula, but in this case, it's very easy to factor. You see, I can factor this as x minus 4 times x minus 1 equal to 0. You see, I can use quadratic formula, but this is faster actually. If I can factor, that would be the best way to do it. And then if I put this factor equal to 0, it gives me x equal to 4. This is one bad value. And if I put the second parenthesis equal to 0, it gives me x equal to 1. This is another bad values. So here are two x values that makes the denominator 0, so they have to be removed from everything else. Of course, if you want to graph your domain, here is 1 hollow and here is 4 hollow point. So that means 1 and 4 are removed. So I have everything from negative infinity all the way to 1. Then I go skip over 1, go from 1 to 4. Then I skip over 4, go from 4 to infinity. Okay. And then you can write it. Domain is set of all x's that x not equal to 1, x not equal to 4. This is one way to write it, but if you want to use interval form, it's quite simple. You start traveling from minus infinity all the way to 1, then you skip over 1, you say union, then you go from 1 to 4, then you skip over 4, then you go union 4 to infinity, and that's your domain. Okay, now another example here. This example actually involves two separate restrictions. Because of the square root, you have to demand 2x plus 4 to be bigger than or equal to 0. So let's see what this one does. So this is 1. The second restriction is that x minus 3 has to be not 0. So I don't want this to be 0. Maybe I should say it, we do not want x minus 3 equal to 0. That's a better way to say it actually. So for 1, 2x plus 4 bigger than or equal to 0, I can subtract 4 from both sides. I get 2x bigger than or equal to negative 4, and then if I divide by 2, this gives me x bigger than or equal to negative 2. This is one restriction. What is the second restriction? Second restriction is that x minus 3 equal to 0. We do not want that. So if I add 3 to both sides, then gives you x equal to 3. So remove this. Then how does it look like? So let's see. First of all, I want everything from negative 2 to infinity. So if I do a solid point here for negative 2, I want everything from negative 2 all the way to infinity. So as I go, I'm going to encounter 3. So this is negative 2, negative 1, 0, 1, and 2, and 3, and 4, and 5. So this is negative 1, 0, 1, 2, 3. So as I go to the right, you see I encounter 3, and I have to remove that. See, I want everything from negative 2 to infinity, but I have to take that out. So that means my domain goes from negative 2 all the way to 3. Then I skip over 3, go from 3 to all the way infinity. Okay. So if you want to write it out, you say domain is set of all x's such that x is bigger than or equal to negative 2 and x not equal to 3. Which is the same thing to say I go from negative 2 to 3, then union from 3 to infinity. So interval notation. The next example, see, so the only time you have to worry about restrictions are when you have a radical sign and a denominator. And in many problems, until we get to logarithmic and exponential form functions, if you don't have a radical sign, or if you don't have a denominator with involving x, then the domain is all of the real lines. So here, no, all values for x are acceptable, because there are no radical sign to produce negative number under the radical sign, and there are no fractions to produce 0 in the denominator. So the domain is from minus infinity to infinity. Okay. So what I would suggest for you guys to do is to maybe look at some of these examples here. Exercise is similar to the ones I worked out for you. So if you really want to master the concepts that we discussed so far, it would be a good idea to work this out before you go to your homework problems. So whatever you choose to do. So please watch this video for section 1.1, maybe once, twice, or 3 times to make sure you understand all the ideas. And then go to your homework, and homework problems would be very much simple and similar to the ones we did. Okay, so pretty soon we're going to discuss section